In this lecture, we are going to do what I call code preparation. It's like the in-between step that will help us get from theory to code. So we know what each of the steps are, and we know conceptually how they work. The next question is, what's the right syntax in PyTorch to actually make it work? I like to think of this like how I think of learning programming languages. I hope everyone in this class knows Python, since that's the language we'll be using. So let's say what I want to do is print the numbers from 0 to 9 inclusive. I know how to do that in Python. It's just for I in range 10, print I. But let's say that now I want to learn how to do this in Java. If you know Java, just pretend that you don't for a moment. What's the situation now? Well, I understand the concept. The only challenge is, what is the Java syntax for it? I know the concept, but I don't know the syntax. So let's look at the syntax. Looking at this, all the components should feel very familiar to you, even if you've never seen it before. I can see the keyword for. That's the same in both languages. That tells me I'm doing a for loop. Same concept, different syntax. I see the index variable I. Again, it's the same concept in both languages. In a for loop, I might have an index variable, something that iterates as the loop progresses. I see a lower limit and an upper limit. The lower limit is 0 and the upper limit is 10, which are inclusive and exclusive respectively. Same thing in Python, except that the lower limit is implicitly 0 in Python, so you don't have to specify it unless you want something other than 0. Finally, I see that inside the loop, we again have the same concept, printing, but again, just with a different syntax. So I hope you get the analogy here, which is that, number 1, concepts and syntax are separate things. You might know the concepts, but in different libraries, the syntax will be different. Number 2, since we already know the concepts, our next task is to ask, what is the syntax? What I want you to realize at this point is that, while this is the most simple script from this course, it is also the most important. You're going to notice a pattern in this course, which is that no matter how complex what we do is, these steps will essentially remain the same. Remember that what we want to focus on right now is, number 1, how do we build the model? Number 2, how do we train the model? And number 3, how do we make predictions using the model? Let's start with number 1, how do we build the model? At this stage, it's going to be very easy. Just one line of code, model equals nn.linear11. What this means is that we want a linear model with one input and one output. The first argument is for the input size, and the second argument is for the output size. There are cases where the input and output might be sizes other than 1 and 1, but we'll see those later. Right now, we're interested in doing simple linear regression, where there is one x-axis and one y-axis. Next up, number 2, how do we train the model? If you've ever used other libraries such as Keras and scikit-learn, you might assume this would be easy in PyTorch, but unfortunately, it doesn't encapsulate all the steps as you would expect. Luckily, thanks to the concepts we just learned, that will help us in understanding this syntax. The first step in training the model is to define a loss and an optimizer. As we discussed, the loss that we need for linear regression is the mean squared error, and there just so happens to be this object called MSE loss in PyTorch. Typically, we call this object a criterion. There's one interesting thing to notice here, which is that this is a bit of an exercise in what I call API hunting. If you think only about the concepts, you know the equation for the MSE loss. If I gave you the y's and the y-hats, you could calculate this loss yourself. But in PyTorch, it's not a matter of knowing the formula. It's a matter of knowing the syntax. So you need to find the right object that implements the loss you were looking for, and then do the right things with that object. At the same time, it's nice to know a little bit about the concepts so that you actually have some sense of what's going on. Next, we have the optimizer. There are many such optimizers in PyTorch, but the simplest one is called SGD. When we create the SGD object, we pass in 2 arguments, the model's parameters, which we get by calling the convenient function model.parameters, and the learning rate. As a side note, SGD stands for stochastic gradient descent. Again, in these lectures, I'm not so concerned about what's going on mathematically, but rather the syntax. If you'd like to understand what's going on mathematically, I would encourage you to check out the in-depth sections of this course. Alright, so at this point, we've defined a loss object and an optimizer object, but we haven't yet done any computation with them. As you recall, gradient descent involves doing a loop, and inside the loop, you repeatedly apply the gradient descent equation. So that's essentially what we want to do right now, but in PyTorch. So obviously, we need a loop. Usually, we call each iteration of the loop an epoch. Unfortunately, it's not so easy as simply translating this one line of mathematical expression into one line of code. There are multiple steps in the code that have to be done. The weirdest part just happens to come first. We have to call optimizer.zeroGrad. At this stage, I like to think of it just as some boilerplate code, something that needs to be done. So just put it there and forget about it. If you want to know what it does, then what we can say is that internally, PyTorch accumulates gradients whenever you call loss.backward, which is a line that shows up later in this loop. Personally, I would not worry about that because 99% of the time, we'll be doing exactly what you see here, and so far, none of the examples in this course require you to actually accumulate gradients. The rest of the steps are relatively straightforward. As you know, in order to calculate the loss, we need the predictions, the y-hats. In order to get those, we pass them into our model. This allows us to see the functional aspect of PyTorch. Even though the variable model is an object of type linear, as you recall that's what we created earlier, it can be used as if it were a function. So when we pass in some inputs into the model and call it like a function, we get the model outputs. The next step is to pass the arguments and the outputs into our criterion, the mean squared error. Again, this is an object, but we're using it like a function. The next step is to call loss.backward. Conceptually, you can think of this as calculating the gradients. For example, the partial derivative of L with respect to M and the partial derivative of L with respect to B. The final step is to actually apply the gradients using the gradient descent equation. As you'll see later, there are a lot of variations to the basic gradient descent, so once you have the gradients, there are a few different things you can do with them aside from just this. Now you may have noticed something strange in the previous code snippet. Previously, I called the data x and y, but in the previous code snippet, I used the variable names inputs and targets. Is this just a matter of some trivial renaming, or did I really mean to say that they are different things? In fact, they are different things. When I load in the data, I usually call the inputs x and the targets y, and usually they are NumPy arrays. But one important detail that we haven't looked at yet is that PyTorch does not work with regular NumPy arrays. Instead, PyTorch works with torch tensors. These are basically arrays, but they are special arrays that are part of the PyTorch library rather than the NumPy library, so they have some special functionality. So some conversion has to take place before you pass the data into your model. In the following example for simple linear regression, the steps are what you see here. First, we're going to reshape x and y to be n by 1 instead of just n. In machine learning, we typically assume that our data is two-dimensional, with the number of samples along the rows and the number of dimensions along the columns. This applies even for the targets, which is not the case in libraries such as Keras or scikit-learn, so be aware of that. Second, PyTorch is really picky about data types. It won't allow you to multiply a float32 by a float64, which is also known as a double, so you have to be mindful of this also. By default, if you don't specify anything, PyTorch will create all your variables as float32s. In NumPy, if you don't specify anything, your arrays will be float64s. So before we create torch tensors, we're going to cast our NumPy arrays into float32. The final step is to call the function torch.fromNumPy. This takes as input our NumPy arrays and returns corresponding torch tensors. So these are the inputs and targets we were working with in the previous training loop. The final step is to make predictions. You might think we already did that in the training loop when we called model of inputs. But the important thing to remember is that PyTorch only works with torch tensors, and the inputs variable is a torch tensor. It's reasonable to assume then that the output is also a torch tensor. Of course, if you want to do any later processing, such as plotting the array with matplotlib, you might want to have a NumPy array rather than a torch tensor. Therefore, in addition to actually calculating the output, you'll also want to convert it back into a NumPy array. Normally, you can do this just using the NumPy function. However, PyTorch also does some stuff behind the scenes, where it creates a graph and keeps track of the gradients in the graph. Basically, you can just call the detach function before you call the NumPy function in order to detach that tensor from the graph. Alright, so that was our code preparation for simple linear regression. I said this before, but it's worth repeating. While this is the simplest example in the course, it's also the most important because it introduces a lot of new concepts, mostly about how to use PyTorch. In future examples, we'll just be repeating these same concepts over and over again, so you'll get lots of practice. You've seen that PyTorch is quite a bit more complicated than simply instantiating a model, calling fit, and then calling predict.